Okay, so now let's try.
Give it a second to make sure the owl is working, and then yes.
Yeah, see, it's still not.
I don't know if my voice would be.
Isn't there a lapel there somewhere?
Yeah, okay, for some reason it just wants to connect to mine.
How I can share my screen?
Yeah.
No, it's
I don't think you'll be able to share because you're using your laptop.
Oh, really? Oh, that's not great. That's so yeah, because there's no.
Yeah, because since it's connected to that, like this device is not now connected to that. It's only using that screen.
That is unfortunate. Make sure it's
it should be just a quick corner there. Thank you. You can double check too. Just go to more real quick. Yeah, pause that. So, and then.
Okay. Unfortunate. Well,
yeah.
Okay.
Okay.
All right. Hey everybody, thanks for joining the EERI seminar series. Today we're welcoming a familiar face, Abdulrahman Taha, here to present his research on, well, the Bayesian inference model. Take it away.
All right, good afternoon, everyone. I think most of you know me. For those who don't, I'm a PhD student in the civil engineering department, and I'm working under the supervision of Dr. Brahimian. And today I'm going to present our work on Bayesian inference for mechanics-based digital twinning of civil infrastructure. So to start, as civil engineers, we usually use digital models or finite element models for different purposes. We use them for structural design and implementation. We also use them for performing performance-based assessment to evaluate the seismic performance of civil infrastructure, and also to plan for retrofit and rehabilitation, and also for rapid post-earthquake assessment, for damage identification, and for decision making. Now, so what we do is that we go from the digital world, from the finite element model, and we perform forward simulation to basically simulate the response of the physical system, and we do all the tasks that I just talked about. Now, the problem with this process is that there are a lot of forms of uncertainties associated with the forward simulation process. Like we have modeling uncertainty. Like when we develop a finite element model, we usually get the data of the system, and most of the time, all these data are not available. And even if they're available, usually we have some missing physics that are not represented in the finite element model. And so all of these basically add to the uncertainty of the response that we get out of the model. Another source of uncertainty is the input. We have certain systems where the input is either unknown or it cannot like accurately be measured. Like in the case where we have soil structure interaction effects, the foundation input motion is not measurable for reasons I'm going to explain later. So basically, to deal with this problem, what we're proposing here is to do model inversion. And the idea is to basically use the recorded response of the physical system and inform the developing of the finite element model. And so basically, through this process, we can estimate the different model parameters. We can estimate, in case of the input motion is not known or is not accurately measured, we can also estimate the input motion. And we can quantify the different sources of uncertainties associated with the developed model. And so basically, the output of this process is what we call a digital twin. And this basically refers to the updated model that we get from the model updating process. And we can use this model to do virtual sensing. And that's what this means is that basically, in the case where we have damage, in a civil infrastructure after earthquake, we can go and inspect the damage physically, but most of the time this process is quite, complicated and not cost effective. And so the idea is that instead of inspecting the physical model, we basically interrogate the updated model and record the responses that we cannot easily get from the physical model. And this is what the virtual here comes from. And then using this updated model, we can basically get information about the damage status of the physical system. So how do we get about this model updating process? We use the Bayesian framework. So basically, we start with recording the response from the physical system, and then we develop an finite element model of the system. And y hat here refers to the predicted response that we get out of the model. And then we define the simulation error, which is basically the discrepancy between the recorded response and the updated, the predicted response for the model. And given that this is a probabilistic framework, we assume that different model parameters to have a normal distribution. And also the same thing for the simulation error, we assume it to have a normal distribution with zero mean and covariance R. And this covariance matrix is a tuning parameter that we use to get the best estimation performance. And then using this information, we can define the likelihood function and incorporate this into the Bayesian formula, where we can basically, calculate the posterior distribution of the model parameters. And then we use this updated distribution to go and define the prior information for the finite element model and keep repeating this process to minimize the discrepancy between the recorded response and the predicted response of the model. And so you can think of it as an optimization problem, basically. So I talked about, estimating the model parameters, but I didn't talk about estimating the input motion in the cases where the input motion is not recorded, like where we have significant cell-structure interaction, or in other cases where the input force, cannot be accurately measured, as in the case of wind turbines. So basically, in these cases, we augment the unknown input with model parameters in an extended model parameter vector. So this vector includes not only the model parameters, but also the unmeasurable or correct, like not accurately measured input motion. And we do the process that I just explained before to now estimate the model parameters and also the input motion times here. So now, before I move to showing some of the applications that we used for this framework, I'm going to just explain some terminologies that I'm going to use later. And it's related to soil structure interaction. Soil structure interaction can be performed using two approaches: the direct approach, where we incorporate both the superstructure and the soil domain in the finite element model. And this process is very computation expensive. And that's why, in practice, people usually use the substructure approach, where we replace the soil domain by springs and dashboards, or what we call the impedance function. However, to develop this model, we need to make some assumptions about the behavior of the soil structure system. And these assumptions, the main assumption is that the solution of the equation of motion of this system can be divided into two steps. The first step is kinematic interaction, where we basically study the effect of structural stiffness on the soil deformation. And so the way we do this, assume that the structure doesn't exist, and we have, seismic wave field incident on the soil domain, and this is what we call the free field motion. Now, if we incorporate a massive structure, it's gonna modify the soil deformation at the interface between the foundation and the soil. And so basically, this is what we call the foundation input motion, which is definitely different from the free field motion. And you remember what I said about the foundation input motion? It's not measurable in the real world because there is no such thing as a massless structure. You cannot, isolate the effects of the structural mass, and that's why the foundation input motion cannot be measured in reality. And then the second step is that we take this foundation input motion applied to the structural base. And so we get the second effect, which is the inertial interaction. Basically, when the structure starts vibrating, it induces some forces on the foundation, and this makes the underlying soil to deform even further. And this is what we call soil flexibility, meaning that we have additional degrees of freedom as the structural base that doesn't exist in the fixed base model of the system. And the other effect is that when the foundation starts vibrating, it basically works as a source of wave radiation, which means that part of the seismic energy in the structure gets propagating back into the soil domain. So this is one damping mechanism, and the other damping mechanism is that the soil deforms non-linearly, and so we get also aesthetic damping. And so basically, soil flexibility and damping are two inertial interaction effects. Now, how we simulate these two effects in the substructure approach? The kinetic interaction, we basically use transfer function that relates the free field motion to the foundation input motion, and then basically use this foundation input motion, apply it to this flexible base model of the structure, and simulate the response of the flexible base system. Now, of course, you can, you might ask like how accurate these models are, and this is also one of the applications that we can use this model updating framework for, to basically validate these models by estimating these transfer functions and impedance functions using the response of physical systems, and then compare it to the analytical solutions of these models in the literature. Okay, so now I'm going to move on to the first application of the model updating framework. This is the American Library building, and this is a 9-story reinforced concrete shear wall building on the Celtic campus. This is the plans for the floors and the foundation, and here this shows where the sensors are installed on the different floors, and also the direction shows the direction of the recorded response in each of these sensors. And the table shows the different sensors and the response it's recording. And in this study, we used the recorded response of the system to the 2002 Yoruba earthquake, and you can see that the magnitude is very small, and that's why we decided to develop a linear elastic model of the building, because we don't expect much non-linearity. So this is a model that we developed in OpenShift. Can be divided into 3 parts. The first part is the superstructure, and it's characterized using 6 different parameters. And then the impedance function, or the soil parameters, and here we have 8 of them. And then the foundation input motion. We only consider the translational components of the free field foundation input motion, because this structure doesn't have, the foundation doesn't have a very embedded depth, and so basically the rotational components can be neglected. And like I said, the foundation motion is not measurable in reality, and so we also estimate those motions along with different model parameters. Okay. One problem with estimating the parameters of this model is that we have a strong correlation between the stiffness-related parameters of the superstructure and stiffness-related parameters of the soil, and the same for the damping. We have a strong correlation between the damping-related parameters of the superstructure and the soil. And so basically, the problem with estimating them in one step is that we might end up overestimating the parameter of the superstructure while underestimating those of the soil, and vice versa. And so we thought about a way to separate the estimation of these different sets of parameters to basically try to avoid this correlation. And the way we did it is that we adopted this approach from the literature. And so basically, if we want to estimate only the parameter of the superstructure and neglect those of the soil, we can use the motion at the base of the superstructure as the input motion, which is the foundation level motion, and the response is basically the response at the top. And so this way we can isolate the effect of the impedance function. So this is the first step, where we only identify the superstructure. The second step is that we use the foundation input motion as the input, and the output is the structural response. And basically, we can, in this step, since we already estimated the superstructure parameters, we can fix the superstructure parameters at the values estimated in the first step and only estimate the impedance function along with the foundation input motion. So we adopted this approach. The first step is we calculate the foundation level motion using the different recorded responses on the foundation, and then perform input-output model updating. And by input-out here, I mean that both the input and the output are known, and they're both used to estimate the superstructure parameter. And so the output from this process is the estimated superstructure parameter. Once we do this, we can move on to the next step, where we can fix the superstructure parameters at the values estimated in the first step, and then include the soil parameters in the model. And then now we can perform out only model updating, meaning that only the output is known and the input is unknown and to be estimated with the superstructure parameter. And so the output is basically the estimated soil parameters and the different components of the foundation input motion. So this video shows the model updating process. The gray curve represents the recorded response, and the red is the estimated response or the response of the estimated model. And then here we have the different model parameters are being updated over time, and here the estimated input motion. As you can see, if you look here, you can see that it takes some time for the response of the model to converge to the recorded response, but probably it's not very obvious because it's very fast. Anyways, and these are the results of the first step. Here I'm normalizing everything with respect to the initial estimate, and then these are the final estimates that we got from the model updating process. And then this is for the second step where we estimate the impedance function parameter. And these are the estimated components of the foundation input motion. This work has been published. You can look at this paper if you're interested. Now, the second application is the Garden Valley test structure. This is a one-story building located in Garden Valley, California. And it's designed specifically for soil structure interaction study. This shows the instrumentation plan of the structure. And this table shows the different sensors and the response they record. Now, this structure is part of the George Brown network for earthquake engineering simulation. And they have a website where the recorded response of this structure is being updated or uploaded on real time here. And so if you go to this website, you can find the recorded response from 2010 up to now. And so basically we use these two recorded responses to use in our model update. First of all, the modeling of the system, the superstructure is a 3D model and developed in OpenSea. And we assume that the unknown parameters to be estimated are those four parameters. This is the elastic models of elasticity of the steel and concrete. And these are the two really damping parameters. Here, the modeling of the impedance function. In this case, we used what's called a limit parameter model from the literature, which is consists of two systems, a base system and a core system. And the difference between this and the model we used in the previous study is that this can model the frequency dependency of the impedance function in the time domain, which of course, it cannot be explicitly modeled, but this model provides an approximation of the frequency dependency of the impedance function. And basically, we defined a model in each vibration direction. So in this case, we have a model in the vertical direction, a model in the two horizontal directions, and another one in the two broken directions. And so we have basically a total of 18 different impedance function parameters. And this table shows the initial estimates for these different parameters. Here are the estimation results from the first step. And here I'm showing basically the results from the first ground motion, and this is from the second one. And here I'm showing the basically comparison between the recorded response in yellow, the response of the initial model in blue and the response of the final model in red. And you can see that there is almost perfect match between the response of the updated model and this compared to the initial model. And these are the results from the second step, along with the estimated components of the foundation input motion. Again, this is a comparison between the recorded response, the response of the initial model, and that of the final model. And the final model can, accurately reproduce the response of the recorded, the recorded response. Now, I was talking at the beginning about the importance of validating these analytical solutions for the impedance function and the kinematic interaction transfer function. And to do that, we did this comparison between our estimation results and the analytical solution for the impedance function. And in this case, we picked the impedance function developed by Bayesian and Cosell. And comparing our results to this impedance function, you can see that there's very good match for the horizontal parameters. However, this is not the case for the rotational parameters. You can see that the model overestimates the rotational stiffness and underestimates the rotational damping. And we think that the reason is that this model is developed for a half-space soil. And this is not really the case for the gamma valley structure, because if you look at the structure of the soil, it can be approximated using 2 layers, not just one homogeneous layer. And another thing is that in this site, the groundwater table reaches the surface in the winter, which is the time of these 2 ground motions. And the problem with the analytical solution is that it doesn't consider the presence of any ground water table at the site. So we also think that this could be another source of discrepancy between the 2 impedance functions. Okay, now the last step is that, you might ask, why do you think that our updated model provides any better approximation of the physical system compared to the analytical solution? And to answer this question, we did this assessment study where we did forward simulation using another seismic motion that was not used in the model updating process. And basically, we're comparing our estimated model in red compared to the recorded response. And this one is another system identification study on the same structure, and this is the analytical solution. And if you look at the response, the Fourier spectra of the responses, you can see that our model, can accurately capture the frequency content of the system, while both the other 2 models overestimate the frequency, which shows that the updated model from our framework can, accurately represent the condition of the structure. Okay. Now, of course, this is not a perfect framework. It has its own limitations. And one of the limitations that I explained in the beginning is that we assumed the simulation error to follow a zero mean Gaussian distribution. Of course, this is a limiting assumption. It can be accurate in certain cases, but also in other cases, it can be violated. And so the idea here is that instead of making these strong assumptions, we decided to basically consider the mean and covariance metrics of the simulation error to be unknown and to be estimated with the different model parameters. And so what this does here is that here we just, like previously, we're just estimating the different model parameters, but then here we're incorporating both the mean and covariance metrics of the simulation error into the estimation process. And so we need basically to estimate this joint probability distribution of the model parameters, the mean and covariance of the simulation error. And so to do this, we need to solve this maximum a posteriori estimation problem, which was divided into two parts, where we estimate the model parameters in the first step and the statistics of the simulation error in the second step. And we ended up with these equations. Of course, I'm not showing all the derivations here. And then we use a fixed point iterations because this is a couple optimization problem, meaning that we start with estimating the model parameters, and then we use the estimates from the model parameters to estimate the statistics of the simulation error, and then use the updated or estimated values from here to go back and estimate the model parameters, and so on and so forth. Now I just applied this. This is a recent work, so I just applied it to a very simple numerical model. And in the future we're gonna try to apply it to more complex numerical models and also to physical systems. Here I'm just using this flexible Bayes single degree freedom model. This is the input motion, and these are the responses of the Bayes and the structure in the horizontal and rotational directions. And so this is assumed to be the true model that represents like a physical system. And then we do the model updating process. Now, sorry, this framework that I just explained, we call it adaptive estimation. We call it adaptive estimation. And so here I'm showing the results for using this new framework. And here, basically, we're assuming that the means follow a sign function. It's not a zero mean anymore, like before. And also the covariance have a half cycle of a sign function. And so you can see that these are updating results. You can see that the framework can accurately capture the statistics of the simulation error. And as you can see that both parameters and the input are being estimated correctly. But comparing it to the non-adaptive estimation framework, the one I was using before, you can see that introducing noise basically messes up with the estimation of both the input and also the model parameters. Which means that if we have a physical system where the noise or the estimation error term doesn't follow the zero mean Gaussian distribution assumption, that this will definitely affect the estimation of the model parameters and the input motion. Like I said, this is very recent work, so we're going to apply it to more complex numerical models and probably a bridge in the future. And that's it for me. Thank you.
Thank you, Abdu. Do we have any questions for him?
Thanks for your presentation. Just please correct me if I'm wrong. As far as I understood, your model tries to update or estimate the parameters based on the measurement that it has and based on some computational efforts that it's been done. And I guess that it's possible that with different sets of parameters, in the case that you don't know the exact value of the parameters that you're estimating, it is possible that with different sets of parameters, you get the exact solutions, right? In that case, have you done any uncertainty quantification for this stuff? For example, with how many sets of different parameters that your model will estimate, or estimate your response would be exact or something like that?
So basically, the what we do here is that like this. We go to the American Library Building. So, like when we started the model updating process, that was not the initial set of parameters that we started with. We started with a very long set of model parameters, almost 15, and then we did an identifiability study, which basically gives you an idea about how much information the response or the recorded response carry about the different model parameters. And so if we see, and that happened in this case, if we see that one of these parameters or some of these parameters don't, get much information from the recorded response, then we fix this parameter at the initial value and only estimate the parameter that show that the response is very sensitive to. Does that answer your question?
Any other questions?
Have you tried this framework on a much rigorous way? I see all the extensions that you go. Have you tried like on a higher
magnitude? Higher magnitude?
Well, your input motion was about 0.003.
Yeah.
And how about the other value? What was the input?
Yeah, it was also the one we find was also like a low magnitude. But so far, no, we haven't used it on any cases large amounts of data.
So you're not exercising the non-linearity of
Yeah, of course. This is what we're not in the future, but the model is like equally applicable to nonlinear models, because we can just develop a nonlinear model, and instead of estimating the linear properties of the model, we will estimate the nonlinear model. So it's equally applicable to nonlinear models, and something we're gonna do in the future.
So something that you know what on.
Follow-up is very low level, very high order capture the soil interaction. So, and we know that actually soil response is 73%. We really know timely, reliable, timely representation given those impedance. So, is there any way to sort of present or somehow not this that address that issue that would be applicable to an approach that does time history and also at the same time in parallel frequency matching?
I mean, like for this one-parameter model, we already did some studies before we like to make sure that it actually can represent the frequency dependency of the infinite function, and it shows like very good accuracy. So it's not very bad, but also I think it could be extended to frequency domain models as well, because it's the same idea. You just define any kind of model you want, parameterize with some unknown parameter vector, and you can estimate these parameters using the recorded response.
To be able to address the soil structure, which actually have to couple with it.
Yeah, so I think that could be one.
Thank you for the questions. We get one more. I can do a question. I'm a little bit confused on one of the examples you had. You said the quantification of the soil parameters. One of the reasons why it may not have been perfect was that the soil may have been saturated or frozen. I'm confused on why, like that change in properties, why isn't that able to be estimated with this model if it's completely frozen?
So, the way the inference function is developed is, that we have this like soil foundation system, but superstructure doesn't exist. And we apply some force on the foundation and record the foundation deformation, and then we use the applied force and deformation to estimate the inference function. It's basically the ratio between the applied force and the plotting deformation.
Okay.
Now the problem is that if you develop this for a certain model, in this case the analytical solutions I used was developed for a homogeneous soil without any groundwater tables. So that gives you a certain impedance function, right? If you change the properties of this soil foundation system in any way, like add groundwater or use a layer soil instead of homogeneous soil, then you will get a completely different impedance function. So each impedance function represents a specific soil foundation system.
Oh, like that instant in time.
Yeah.
That's all. I see.
It was frozen, right?
It says like groundwater. No, it said like a groundwater or frozen.
Yeah, because it sounded like it was in winter, so maybe a little frozen.
No, it's not frozen. It's
Just water.
Just water.
Oh, I misheard. My bad.
But the same problem, like if you have kids where there's any like frozen soil, of course it will deviate from the.
You just need that snapshot then.
Yeah, exactly.
All right. Any other questions from anybody? Not seeing any questions on Zoom either. So with that, well, thank you so much for your time, Abdul.
Thank you.
Eat the pizza. That was good. That was really good. I like it.
Let's do that next time.